In this video, we're going to use what we've learned so far about self-type to incorporate self-type into the type checking rules for COOL. First, let's remind ourselves what the type checking rules for COOL actually prove. So the sentences in the type logic look like this, and they prove things of the form that some expression has some type, and they do that under the assumption that object identifiers have some types given by O, methods have signatures given by M, and the enclosing class, the current class in which E sits, in which we're doing our type checking, is class C. And the whole reason for this additional piece here, we haven't actually discussed this before, why we needed this C, it is because self-type's meaning depends on the enclosing class. So if you recall that we introduced this notation, self-type sub C, to record in what class a particular occurrence of self-type sits, and this C in the environment is exactly that subscript. It is tracking what class we are in, so when we see an occurrence of self-type, we know what kind of self-type we're talking about. So now we're ready to actually give the type rules that use self-type, and for the most part this is really easy because the rules just remain the same. That is, they look the same, but they're actually a little bit different because they use the new subtyping and least upper bound operations that we defined before. So for example, here is the rule for assignment, and this looks identical to the rule for assignment that we discussed several videos ago. But notice that this use of subtyping here is now the extended definition of subtyping to incorporate self-type, and so now this rule works with self-type as well as with the normal class names. Now, there are some rules that have to change in the presence of self-type, and in particular, the dispatch rules need to be updated. So here is the old rule for dynamic dispatch, and this rule, this part of the rule, actually doesn't change. It stays the same. But I just want to point out the essential restriction in this rule is that the return type of the method could not be self-type. And that's actually the place where self-type buys us something. So the whole purpose of having self-type is to have methods whose return type is self-type, because that's where we actually get the extra expressive power. And now we have to consider the case, now that we have self-type and we've done all this work, what if the method's return type is self-type? How are we going to type check that? Well, here's the rule. So as usual, we type check the expression that we're dispatching to, that's E0, and all of the arguments, and we just get their types. And they're just type checked in the same environment as the entire expression. And now, just like before, we look up in class T0, the type of E0, the method f, and we get its signature. Okay? And then we have to check that the arguments conform, that every actual argument, E1 through En, has a type that's compatible with the corresponding formal parameter in the method signature. And if all of that works out, then we can say that this dispatch is going to have type, oh look, T0. So where did that come from? Well, the return type is self-type, and so the result of this entire dispatch is going to be the type of whatever E0 was. E0 is the self parameter, and whatever type we got for E0, that is a sound static type for the result of the entire expression. So we simply use the type of E0 as the type of the entire the entire dynamic dispatch. Now recall, the formal parameters of a function cannot have type self-type, but the actual arguments can have type self-type, and the extended subtyping relationship will handle that case just fine. One interesting detail is that the dispatch expression itself could have a type self-type. And so what do I mean by that? Well, let's think about E0 dispatching to method f. And then what happens if E0 has type self-type? What if we can prove that E0 has type self-type? And the problem here is that we need to look up in the M environment, in the method environment, in some class, the definition of, or the signature of method f. We have to get back that type signature so that we can do the rest of the type checking. And if E0 has type self-type, normally we use the type of E0 to do that lookup. What type do we use here? Well, if this whole thing is occurring in class C, if we're type checking in class C, let me just put the line there, then it's safe. Then this is a self-type sub C, and as always, it's safe to replace self-type sub C by C, and so we'll just use the class C there, the current class that we are type checking in to look up the method name f. We have to make similar changes to the rule for static dispatch. So here is the original rule for static dispatch, and again, this part of the rule will not change. This handles the case where the return type of the method is not self-type. But if the return type of the method is self-type, then the rule looks a little bit different. So once again, we type check the expression that we're dispatching to and all the arguments in the same environment as that of the entire expression. We have to check that the class we're dispatching to, the type T0, is a subtype of the class named in the static dispatch. We have to look up the method. It has to exist in that class that we're statically dispatching to. So we have to look up in class T the method f and get its signature. And then we have to check that the actual arguments conform to the formal parameters, that their types, the types of the arguments match the declared types of the formal parameters. And then the only thing that's kind of curious about this rule is that the result type here is again T0. And why is that right? It could have been a T. It could have been the type to which we statically dispatched. And it's not, because self-type is the type of the self parameter. And even though we're dispatching to a method in class T, the self parameter still has type T0. And recall that T0 is a subtype of T. So we use the static dispatch to reach a method definition that's hidden potentially by overridden methods in the subclasses. But that doesn't change the type of the self parameter. The self parameter still has type T0, even though we're running a method in a superclass of T0. There are two new rules for self-type. One involves the self-object. So the self-object has type self-type sub C. And notice that this is one of those places where we need to know the enclosing class so we know what kind of self-type we're referring to. And similarly, there's a rule for allocating something of type self-type. So the expression new self-type also produces something of type self-type sub C. To wrap up this video, here are a few comments on implementing type checking in the presence of self-type. First of all, the extended subtyping and least upper bound operations can do a lot of the work. If you extend subtyping and least upper bound in the way that we did, then a lot of the rules don't have to change, and for the most part, you don't have to do anything special for self-type. Self-type can only be used in a very few places in the language, and it's up to you to check that it isn't used anywhere else. Those restrictions have to be followed carefully. And finally, for the most part, a use of self-type always refers to any subtype of the current class. There is one exception to this in the type checking of dispatch. In dispatch, there's a method lookup where we look up in some class C a method f, and it's possible that that method will have a return type self-type. And this class here, C, may have nothing to do with the current class. We're dispatching here to a different class, and whatever our current class is, this particular self-type refers to self-type in that class, the class in which we're doing the lookup, not whatever class in which we're doing type checking. And fortunately, we never need to compare that self-type to any self-type in the current class, so there's no crosstalk between different kinds of self-type. And again, this is the only place in the type checking rules where you look at a self-type that is not one in the current class. To summarize our discussion of self-type, self-type is still a research idea. It adds more expressiveness to the type system, and I think that's easy to see, but you won't find self-type in mainstream languages. Self-type by itself, I think, is not so important, except for the project that you're going to implement. Rather, the reason for including self-type is to illustrate that type checking can be quite subtle. It's not all int plus int equals int. There actually are fairly sophisticated things and fairly sophisticated reasoning that goes on inside of type checking. In practice, of course, there needs to be a balance between the complexity of the type system and its expressiveness. More complex type systems are harder to learn and they're harder to use effectively, but they also allow you to write more programs.